But at that time, we were already dreaming of making the phone to be foldable, like a thin sheet of paper. And of course, at that time, nobody thought about even there's smartphone we can hold and take everywhere, and internet just started. But then we thought that this future direction would potentially enable a lot of new possibilities. And that was 1995. Now, almost 2025, almost 30 years later, now we just start to see foldable smartphone, right, on the market. And there's the Samsung version and the other versions that are on the market. So I think after having seen or having been doing research for a long period of time, now I really see how long it takes for a technology to really kind of get accepted. It wasn't the foldable phone is on the market only 30 years later, not because the technology wasn't ready. The technology, I would say, was ready probably 10 years ago. But there's also the market driving force that determines whether something become actually commercialized at larger scale because the market ultimately drives the product adoption. So all these are combined together. So that's why I think for any disruptive new technology, the time frame might be 10, 20 years, and especially for hardware development and materials development, it takes a long time to validate, to refine, and to finally also find the right market for the product for it to be largely adopted. The Schön's scandal was about 20 years ago, and there were a series of papers where he was the lead author who carried out experiments, and then eventually the experiments could not be repeated, and also there were fabrication of data through some investigations of the figures. In my case, in particular, I had two papers. I was a co-author with him, but not as senior author. I was a collaborator who my responsibility was to provide the materials to him, and he incorporated the materials into devices he made. And in one case, he observed superconductivity, and another case, he observed measurement of charge transport through single molecules using both cases using materials that I provided. And it was, of course, very shocking when this was brought into investigation because prior to that, there was no indication that he would have fabricated the data. In my case, he actually carried out the experiments in Germany while he was waiting for a visa. I remember sending samples to him. And I asked him to take back the devices so that we can also test them in Bell Labs. The one alarm, one thing was alarming at the time was that when he came back, I asked him where the devices are. Can we take a look? He said, "Oh, they were all broken in his suitcase." That was a little bit strange. But then a few months later, all the fabricated data things were found by others. My name is Zhenan. I'm a professor at Stanford Chemical Engineering Department, also courtesy appointment with material science and engineering and also chemistry. I directed the Stanford Wearable Electronics Initiative.
Well, let us go first. What do you see the main challenges or problem when it comes to what you do in your lab? And I think that's something even of robotics very relevant to. Can you tell me about the challenges or problem that you're trying to solve first?
Yeah, so for soft robotics, that means the robot is not rigid and they're soft and can change shape. And then that means the sensors and electronics also need to be able to adapt to the shape change when the robot moves around or manipulate objects. But the current electronics are rigid and brittle. They are difficult to stretch, especially they can bend potentially, but they are very difficult to stretch or change shape. So my group develops materials, electronic materials that can enable us to make sensors that are soft and shape changeable, as well as the integrate circuits that can potentially be applied to soft robots.
Can I ask you about, because you mentioned many times about the saying that you wish in the design, like being stretchable, self-healing, and damping. And can you tell me about the criteria and the design in your expertise, how you combine the best of the two worlds to have the characteristic you look for in the electronic scale? Yeah.
Right. Yeah. When you first hear it, it may sound impossible for electronics, and the core for the electronics are the materials used to build them. At first, it may sound almost impossible to build all the required functionalities into electronics, but that's precise the fundamental research that we perform. Basically, we first try to figure out how we can come up with electronic materials that have uncompromised electronic properties. So basically, they need to have semiconducting properties similar to amorphous silicon or polysilicon, and then also conductivity similar as metal or close to that of metal. But at the same time, they are stretchy or even self-healable. And then once we have the materials, we can move to the figuring out how to incorporate them into electronic devices, and then finally build the systems from them.
May I ask you, do you find there's trade-offs when you're trying to combine two different characteristics in the design? Because you build polymers, and do you think there's a trade-off? Like, for example, what I'm familiar with self-healing and toughness, for example, is this a trade-off?
Oh, yes.
Do you have sometimes to compromise?
The trade-off is usually if we combine the two properties, and then you get two properties, but then trade-off is each of the properties become worse compared to when you combine. So that's the trade-off, and that's also precisely where the exciting part about the research is that what we are trying to do is to trying to figure out how we can design materials so that we don't have this trade-off. We can have both properties to maintain the same or even be enhanced when we combine two properties together. So we approach this from two aspects. One is we try to understand from molecular level what impacts the charge transport of electronic material and what impact the ability for materials to self-heal. Basically, when I talk about self-healing, that means the materials can have chemical bonds that can break but can recover under room temperature or at a certain desirable temperature. So first, we need to understand from molecular level what are the molecular features that makes a material a good good semiconductor or makes a material a good self-healing material. And then when we put them together, initially we found that when we mix the two together, the semiconducting material become less semiconducting. Basically, the charge transfer become much worse. And then the self-healing material couldn't self-heal that well because the semiconductor cannot heal. And then it prevent the entire material to heal. But we made an important discovery in 2017, which was reported in 2017 science paper, where we found that when we choose the two materials strategically, then the self-healing material can induce nanostructure formation in the semiconductor. So that basically force the semiconducting molecules to become more planar and less bending. And then as a result, actually the charge transport improved because we removed the conformational disorder from the semiconductor. And then on the other hand, the semiconductor forms this nanostructure. The nanostructure is interwoven with the self-healing material. So when the semiconductor become nanomaterial, then the self-healing property doesn't get prohibited anymore. The matrix is still the self-healing material. And we made another discovery a few years later that if the matrix is self-healable, it has a dynamic feature. Basically, the molecules can move around. But this dynamic feature can be transferred into the nanomaterials. So basically, the matrix material can carry the semiconductor material around. If there's a crack, the semiconductor material breaks, the connection is lost. But then the matrix can carry the nanomaterial across this crack and then recover the semiconducting property. So then these discoveries allowed us to now have self-healable electronic materials. And then for stretchability, we have a matrix that's stretchable that induces the semiconductor nanostructure. Or even the biodegradability, we can use a biodegradable matrix and then combined with the semiconductor nanostructure. So this becomes a broad method that's applicable to most of the electronic polymer semiconductors and conductors, and with enhanced electronic property while we add the new functionality.
Very interesting. I want to ask you about also because I think your background is very interesting. You have been in Bell Labs and also for venture capitalists in Silicon Valley. So I think that's give you a little bit of what is needed for real world application here. When you designed this in the lab, are you targeted by the application or just the fundamentals?
It's kind of iterative. Initially when we set the goal to make electronics like skin, it's a very kind of futuristic goal. And I know that it's going to take maybe 20 years or even longer to actually make this potentially into commercial realm. But that's precisely what I want to have. That is a long-term goal we can work towards. And then that drives the thinking about fundamental research and also ideas that we wouldn't have thought about if we didn't have a bigger goal. So then when we actually develop strategies or solutions for the problem, we start from the fundamental side. We start from understanding of the molecules, the materials in the solid state, and then also understand the interfaces of these of different materials and the interfaces when these materials are incorporated into electronic devices. So all these fundamental understanding allows us to then be able to realize the material. And then once we have them, then we start to set additional goals that are more more targeted. For example, building an integrated circuit with this certain number of transistors, with a circuit block has this functions, and then that becomes our kind of target, more application-oriented goal. And then once we realize that, then we can start to think about systems, and systems that can be potentially enabled by the capability of circuits that we're able to build, combined with sensors that we're able to have. And then we can start to think, okay, this soft robot, if I have this circuit and this sensor, what will be the type of control we can have with the soft robot, or what kind of manipulation this soft robot would be able to do to the object it encounters. So then it becomes more towards asking questions that are more practical. Yeah. So there are different stages of research that we carry out, and then in turn, when we actually incorporate these devices into the soft robot or medical devices, so we also are interested in that. Then when we incorporate them into the actual practical systems, then we start to find additional challenges and gaps. And then usually we pick the bigger gaps to address, because then again, we have interesting fundamental problems to work on. So that's how we think about research projects.
Mm. Awesome. Maybe quickly about we mentioned about number of years, 20 years, because of your experience, because you really have interesting background. I will go for this now. But quickly, how do you estimate the number of years? And can you tell me how this is going, just to say will be the next 10 years? Which basis this could be decided?
Yeah, I worked in biolabs before, and at that time it was I started there in 1995. That's the time before we even know what smartphone was. And that time the wireless phone was like the huge telephone, and Apple computer was Macintosh. It just came out. But at that time, we were already dreaming of making the phone to be foldable, like a thin sheet of paper. And of course, at that time, nobody thought about even there's smartphone we can hold and take everywhere, and internet just started. But then we thought that this future direction would potentially enable a lot of new possibilities. And that was 1995. Now, almost 2025, almost 30 years later, now we just start to see foldable smartphone, right, on the market. And there's the Samsung version and the other versions that are on the market. So I think after having seen or having been doing research for a long period of time, now I really see how long it takes for a technology to really kind of get accepted. It wasn't the foldable phone is on the market only 30 years later, not because the technology wasn't ready. The technology, I would say, was ready probably 10 years ago. But there's also the market driving force that determines whether something become actually commercialized at larger scale, because the market ultimately drives the product adoption. So all these are combined together. So that's why I think for any disruptive new technology, the time frame might be 10, 20 years, and especially for hardware development and materials development, it takes a long time to validate, to refine, and to finally also find the right market for the product for it to be largely adopted.
Maybe I want to ask you, you declined the postdoc. I think that's where you joined the labs. I'm really curious about that. When you declined your postdoc at UC Berkeley to join the labs, what made you make this decision? And what did you learn at the labs? I think you mentioned some of that. But when you compare this to academia, you have the two perspectives from Bell Labs and academia. Can you tell me about at this time, why did you decline the postdoc offer and join Bell Labs? I think that was interesting.
Oh, well, I think like many young people at the time when I got my PhD, I wasn't sure what I wanted to do. I kind of looked for postdoc position, looked for industry job, and also I never had any industrial experience. At the end of my PhD. So I also felt the kind of a burning desire also to know what it's like to work in industry. So when I got the job offer from Bell Labs and also knowing that there is possibility to go back to academia, from there because they had lots of Nobel Prize winners and also lots of people go through Bell Labs and later either go to other companies or go back to academia. So I thought that would be a option where I have the flexibility to choose after working there for a few years. And I felt that was really one of the best decisions I made for my career. And I learned so much in Bell Labs, and I met so many fantastic people and great people there. And I learned tremendously about how to think about kind of setting research directions and how to approach collaborative research, interdisciplinary research, and also gain the support or network from kind of the bigger network of Bell Labs. So that was really a tremendous experience for me.
I don't know if you would love to answer this question or not, but I'm curious about the Schön scandal experience. Did you have any, like, as a scientist, like, impact when?
Yeah, so the Schön's scandal was about 20 years ago, and there were a series of papers where he was the lead author who carried out experiments, and then eventually the experiments could not be repeated, and also there were fabrication of data through some investigations of the figures. In my case, in particular, I had two papers. I was a co-author. With him, but not as senior author. I was a collaborator who my responsibility was to provide the materials to him, and he incorporated the materials into devices he made. And in one case, he observed superconductivity, and another case, he observed measurement of charge transport through single molecules using both cases using materials that I provided. And it was, of course, very shocking when this was brought into investigation because prior to that there was no indication that he would have fabricated the data. In my case, he actually carried out the experiments in Germany while he was waiting for a visa. I remember sending samples to him, and I asked him to take back the devices so that we can also test them in Bell Labs. The one alarm one thing was alarming at the time was that when he came back, I asked him where the devices are. Can we take a look? He said, "Oh, they were all broken in his suitcase." That was a little bit strange. But then a few months later, all the fabricated data things were found by others, and it was really shocking because I think as collaborator or for me to work on interdisciplinary research, I fully trust my co-workers and collaborators on what they do. And it's very shocking and also disturbing and made me angry that someone would do such kind of thing. But on the other hand, I think even though after going through such a dramatic experience, I still believe in collaboration because I think to have true collaboration, we have to trust our collaborators. Otherwise, it's impossible to collaborate openly and also collaborate in a true collegial and a team together. So that's still the philosophy I take. And I think, but also at the same time, I think it's important, even if I'm collaborating with others, I should still understand or make the best effort to try to understand what my collaborators do. It's not to trust them, but to be able to really understand the full picture, and also to allow me to also to think that if certain observations doesn't make sense, I'm able to ask the right questions to ensure the science that we do is accurate, is precise, and yeah. So that's the lesson I learned from it.
Given what you said, because you mentioned a lot of interesting point, and especially in the research you do, how you ask the right question. Do you think in the field, maybe because you have multiple experience here, that when you look for the current state of research, especially of robotics, for example, do you think there's something missing? Like we don't ask the right question, why we don't fix this research line? Do you think there's something still need to be considered, like asking the right question? Do you think that we do that, or still there's something missing?
Yeah, I think the to define which path to go to move forward with, or which direction to go, it requires us to ask the right questions so that we can gather the information on what are the knowledge gaps or what are the technology gaps, and have a good understanding on what precisely have been done before and what precisely are things that have not been done. And if a work has, because frequently we hear in the news say, sounds like, oh, this work solved all the problems, and or this work is the first, that work is the first. But when asking the question is to really figure out what exactly is the new thing that this work actually has done, has achieved. It's important, at least for me, to make a decision on what is really hasn't been done or hasn't been achieved, so that then we can select the right path to focus on the path that will give us the biggest impact if we spend time on working on that direction. So maybe that's a long answer to your short question, but asking question is really to gather information so that we can make a decision.
Maybe I want to also ask you about I think something interesting you mentioned about the implant for mental health. I think that's very pretty cool that if we have something, but I know that it's still rigid. But can you tell me about how do you envision this idea that you already have, I think, an initial prototype or something for to, yeah. Can you tell me what are you aiming for and where do you think this could be deployed like for mental health situation here?
Yeah, so initially I learned about the problem. So basically what we are working on is to develop wearables that can give quantitative measurement of data that psychiatrists can use for determining the type of depression that the patient experience and be able to prescribe the right treatment method. And I first learned about the challenge through a interdisciplinary workshop that Stanford School of Engineering organized to promote people from different disciplines to collaborate, to work together. And I learned from psychiatrists that currently for them to diagnose depression, anxiety is basically by asking questions to patient. There's no quantitative measurement. And then frequently when prescribing the medication, it takes sometimes many months or even years of trying different medications slowly to figure out the right one to use. And at the meantime, it's very frustrating for the patient. And depression and anxiety related suicide is extremely widely spread. And 1 in 5 Americans actually suffer from depression, and suicide, deaths due to depression-related suicide actually is more than people killed by cancer every year. So I learned about it, and I thought this is really important problem. And we have been developing sensors that could potentially contribute to this challenge. So we have that's why we choose to work on this direction. Yeah. Yeah, it's a long-term project. Basically, for example, this is kind of similar to having blood sugar level testing, glucose testing for blood continuously. But in this case, we're testing stress hormone continuously. And for the wearable glucose patch, it builds on like 2 decades of development of glucose sensors. And then eventually now there are these commercialized wearable patches. But for stress hormone detection, using simple method and especially continuous method to detect them is only started very recently. So it's going to take some time to really come up with sensors that are reliable and also sensitive and selective enough for this purpose. But that's the kind of problem I think we should be working on in academia because we are trying to solve long-term, bigger challenges.
Yeah. Maybe a few questions for you left. Can you tell me about the challenges that you face? You have been, I think, many years working on in these areas, but what means still challenging for you when you're trying to think about the next thing? Can you tell me about the challenges? Like, in I don't know what kind of challenges or something makes you like, I want to solve this, or with your group. Can you tell me what are the things that makes you yeah, stay up late and thinking sometimes about these problems?
Yeah, well, all the problems we work on are very long term. So I talked about making circuits and sensors for soft robots, and we talked about sensors for wearable sensors for mental health quantification. And the long-term project actually got me started in this whole area was to try to build a electronic skin that can uh, can have sense of touch similar to human skin, and then can directly communicate with the human brain. So we have been working towards this for already many years, but still a lot of work to do. Our latest version that was published earlier this year is our Generation 3 electronic skin, where we have sensors and also the integrated circuit that's used to convert the sensing signal into basically digital signal, like a spike train signal. And we showed that we could directly use the signal to stimulate brain, and then the motor cortex region of the brain would fire electrical signal to control muscle. So now we have one sensor and one circuit built, and then our hand has uh, tens of thousands of sensors. So the next challenge for us is how do we really build a e-skin that can cover the whole hand? And then can we also incorporate some neuromorphic computing hardware into this to be able to put out signal that actually directly test with patient who may have neurostimulator at the peripheral nerve to test out our e-ski. So that's a direction I'm very excited about, and we're actively pursuing.
If you look at the future saying here, is it embedded in daily clothes, or which setting do you think we should use these devices like?
Yeah, I think which setting the devices are incorporated really depends on what their use cases are and what they are intended for. For example, if it's more for monitoring during daily routine, then people probably will not want to have something implanted or even put on their skin all the time. They have to put on and peel off. Probably incorporating into the clothes they wear would be more likely to be adopted. But then on the other hand, if it's for medical treatment purpose, then we need the signal to be very accurate in order to perform the right procedure or treatment, either through electrical stimulation or through drug release. So their accuracy is important. And then for greater accuracy, then we need the sensing device to be close to the body or even be inside the body, because that's where the information comes from. But for disease treatment, if it's a severe disease, people will be willing to go through the trouble to use such devices. So I think it really depends on the use case.
So, Sense maybe I want to ask you, what are things you find very interesting in soft sensors design so far? Maybe beyond your lab, like interesting things you found so far about soft sensor design and soft robotics. Do you have any examples like you found quite interesting?
Mm. Yeah, I find that the work by several groups, such as Renee Zhao, Xuan He Zhao from Renee Zhao is from Stanford, and Xuan He is from
MIT.
MIT. Yeah, and also Matty in Max Planck Institute. They are combining soft robots with magnetic materials, so that then they can guide the navigation of such robots, kind of wirelessly and remotely, which is really cool. And that's why we started collaborating with Renee Zhao's group in our recent paper on the self-healing robots. Basically, we designed materials that can recognize each other. So only the material they will only heal with the right counterpart. So when we have electronic devices, imagine we're going to have multiple layers of different materials. And then if we wanted them to self-heal, they have to recognize conductors. They have to match up with conductor, semiconductor with semiconductor. So we came up with the molecular design to achieve that. And then with Renee Zhao's group, we were able to show a small kind of a soft one-dimensional structure that initially were small pieces, but then under magnetic field, these pieces will dance around and find each other, and then they heal with the right counterpart, and then become a long string that's soft and stretchable. So then you can start to imagine having functional components that can assemble into a system, basically combining the navigation together with intelligent materials design.
Do you think about something in the future like features? I don't know. We have mentioned self-healing, maybe it's stretchability. You wish something like feature in the devices you develop?
Well, since I am more of a materials person, so I like to design intelligence into the materials. So the other than sensing and signal processing using materials, then also movement can be like actuation or muscle kind of movement can be incorporated into materials. So we are working on some materials that are have behavior similar to muscle. So then that would be very useful for soft robotic, because then these are going to provide in addition to magnetic field to control the movement, but then these materials can have muscle to also be used to move the soft robot. So basically, we make the material to be able to contract upon heating and then expand upon cooling. Yeah.
Mhm. Okay, okay. And just think about the maybe quick question here, a follow up about the applicability, since you mentioned about commercial world. Do you think that, for example, heating here and cooling down should be replaced in the future use cases to achieve the task that should be like act as a muscle? Do you think the part of being adaptable and applicable and compact in size? Do you think maybe the techniques we use, for example, the cooling and heating, could be used in commercial setting, or we have to reinvent everything to achieve the goal?
Well, I usually initially we try not to have to invent everything in order for something to be applied. Then in that case, we will find the use cases where we don't have to invent the heater and the cooler. And then, if the currently heating is not a problem, cooling is the bigger problem. To cool down fast is not easy to do. So that is something that then this becomes potentially a driver for a new research branch. Yeah. So, but then yeah, it depends on really what is the biggest bottleneck. And then yeah, for me, I would choose the bigger bottleneck to focus on usually.
Since you mentioned achieving intelligence in the material, we speak sometimes about morphological computation or achieving intelligence through morphology. Do you think material is more significant in that way compared to morphology, using the morphology of the material?
To build an intelligent system, then we really need to think in a system level. What's the requirement for the
Mm.
system, and what's the power requirement and cost and everything. So I wouldn't say one is more important than the other in an absolute sense, because it all depends on what is the system level requirement. But then from research, each field can really try to push the limit for their own field. And then people who do system design, they have all the choices that are laid out for them. And depending on their design criteria, then they can pick the appropriate material, appropriate building blocks, and also device structure and architecture to incorporate.
I don't know if you have any final words for like some people listening or people say for robotic community. Any final words like say?
Uh, well, just focus on bigger problems, identify what are the biggest challenge, and devote your effort to them.
Excellent. Thanks so much. It was really great talking to you. I appreciate it. Thanks so much.
Sure, sure.